Welcome to the event. This is the first artificial intelligence event for Latin America, so welcome.
Muchas gracias, muito obrigado for those who speak Portuguese. I am grateful we'll be using English because my pronunciation of everything else is terrible. So I'm excited to be here today to meet with you and talk about a pretty exciting topic.
Excellent, excellent. And hold on one second. I think we have Mo. Well, anyway, so the topic for today is about, I mean, something very, very interesting is the use of AI for privacy. And how does that work? I mean, how
does that work?
Yeah, exactly.
That is the big, right? So what I was hoping we could talk about today, and I prepared a little material, so maybe we'll go through that in a minute after we set the stage. But I think what we really need to talk about is a civilization is a set of global concerned people about lots of major issues going on in the world today. We know that AI is increasingly becoming important and transformative for business, but we also recognize increasingly that privacy matters, and being able to use advanced technology while preserving some aspects of privacy is really going to be a foundational way that AI changes going forward, I think. And so the technology that I want to talk about today broadly is privacy preserving AI, but I'm going to focus more specifically on a particular approach to that called homomorphic encryption. But I want to be clear to the audience that homomorphic encryption is not the only way to solve this kind of problem. And I think if there's any one takeaway that we should focus on, it's that privacy preserving AI is a thing. It's very new in a lot of areas, but really the time is right to start building skills in that area. So whether you have practitioners or folks that are running businesses and trying to learn how to apply this tech, the time is right to start reaching out to your trusted advisors and really kind of getting your head around this concept. Because when we move past AI that works into ethical AI, ethical and privacy preserving AI, I think, is the next way where we can have all of the benefits with minimizing the risk.
So how long have you been working on this privacy AI?
It's a good question. So my first exposure to homomorphic encryption was actually almost a decade ago. But in terms of focusing in the AI space, my academic background has been in AI for almost 20 years. But those two roadmaps didn't meet until a few years ago. And it's funny you should ask, because one of the reasons that this technology has not taken the world by storm, and why we don't see privacy preserving AI and homomorphic encryption AI in practice everywhere, is that the tech is relatively new on the homomorphic encryption front, and the performance over the last, say, 11 to 15 years from when it was sort of first pioneered by Craig Gentry. I think the performance is really slow, and that's why it hasn't taken off like wildfire. But every year we see this exponential level of performance improvement, from algorithmic techniques to folks that are just thinking about problem decomposition and parallelization, and really extracting a lot of value from it. And it's interesting that in the last 2 years, some AI inferencing use cases, which tend to be pretty high on the list of things people might want to do with this technology, have become fast enough that they're viable, and you could actually run them in production if someone was so inclined. And in fact, there's a lot of forward-thinking companies out there that have made partnerships with the tech firms that are kind of specializing in this to build their proof of concepts, their pilots. There's some government agencies looking at this stuff, obviously. But the real confluence of AI plus this privacy preserving stuff is really kind of new the last couple of years. And that's effectively as long as I've been in the privacy preserving AI space. But again, I have a background in AI that goes back quite a bit.
Right. You worked in the past. You're a Deloitte now. You're a Deloitte fellow right now. And in the past, you were one of the biggest AI companies in the world, IBM, correct? So
yeah. So my academic career, I studied AI, and then I went to IBM, where I worked on the enterprise software space for a long time with a bunch of great folks working on really great enterprise software, mainframe technology, things like that. Had a great time at IBM. Worked in that space for quite a while. Went back to get a PhD while I was working at IBM, and they graciously sponsored me to get my PhD through their learning program. Thank you, IBM. And I did my PhD in applied artificial intelligence for cloud computing. And along the way, I had switched into the IBM research division, where I worked on a variety of interesting AI at the edge cases. And then also at a certain point, I actually ran an incubator as the technical lead for advanced technology. Did a bunch of interesting AI demos and found ways to find AI tech a home into products and services. So yeah, I was with IBM for almost 20 years, and I just joined Deloitte earlier this year as a tech fellow, which is a career destination. A lot of people don't know about it, so if I can indulge for just a moment.
Sure.
It's a career destination within the Deloitte firm for folks that want to be technical. So a lot of people know about principals, partners, managing directors, if you're in the consulting space. There is a home and a career track for folks that want to be deeply technical. And I'm just here to say that, it's not just the Googles, the Facebooks. There's some real serious long-term career investment to be made at consulting firms. And obviously, Deloitte is one of them. So thank you to my current employer for giving me the opportunity to come and speak with you today.
Come join us at Deloitte. So it's a great place to work.
We're hiring. That's a process.
And later on, we have another Deloitte representative. But so just to make sure this is not a Deloitte event, so just get that out of the way for the lawyers, because our lawyers love that stuff. So yesterday we had a really nice panel that was focusing on fintech, right? And one of the issues that they discussed, which is the issue that affects everyone, is privacy, right? Privacy is driving a lot of the advancements, but it's also making it very difficult. It complicates a lot of things, because you have privacy is not just I'm going to put privacy here. It's got a lot of stuff, and then we start talking about homomorphic encryption and all that stuff, and I'm like, what is that? So can we take a step back and guide us through exactly what it is, the technology, and then let's review some use cases for that?
Yeah, let me go ahead and pull up a presentation I prepared for this. Let me go ahead and just get this set up here. Okay.
You should be able, yeah.
Yeah, I just want to make sure I'm sharing properly. Oh, it says I can't. That's interesting. It says failed to start.
Oh, well, you are a co-host.
Interesting. Technical challenges, imagine that.
There you go. We need some AI over here too.
Well, let's see if there's another way to share it.
There we go.
All right. Is that working? I apologize. I think
that's perfect.
Let me see if I can get this in presentation mode, just so that you guys can see a little bit better. How's that looking?
That's perfect.
Okay. Apologies to the audience for the.
No, that's all right.
We got it figured out. As soon as you brought in AI, magically. All right. So let me just give a quick overview, and I promise not to make this too long. I think it's maybe 8 or 9 slides or something like that. Okay. So I just want to kind of talk through the concept to address your question, like what exactly is homomorphic encryption? Why is this something relevant to AI? And talk about some of those use cases. And so then we'll turn it back to an open discussion maybe at the end. And feel free.
I'll step away. I'll step away and let you drive, and then I'll join you back.
Okay. Okay, so right here, I want to just begin. This is our roadmap for what we're going to talk about. We're going to talk about fully homomorphic encryption as a concept and what that means. Definitely talk about some of those use cases that matter in our practical today and kind of where they might be in the near future. And then I think we want to have a bit of a dialogue about a privacy preserving AI future and what that could look like. And I do welcome questions from the audience. I'm sure we've got a lot of really bright folks there with a lot of interesting business challenges. And so we would love to hear from you through the conference venue. So let's begin by asking a bit of a rhetorical question, okay? So if you ask yourself, what if your sensitive data stayed encrypted even during AI inferencing? What could you do that you could not do today? So we're all very familiar with the concept of AI model training now, where we take plain text data, usually numerical, sometimes image data, whatever, and we do model training on that and come up with something that can then be used for inference later. So we can ask questions of the model. That entire process is done in the plain text or in the clear today. But what if instead we could actually keep the data that we would send to the model fully encrypted? So instead of sending in a set of unencrypted feature vectors to have a decision made by an AI oracle, what if we could send my data encrypted so that the model didn't know what I was asking it, but could still give me a proper trained AI response? And that's one of the things we like to think about with privacy preserving AI, is protecting the privacy of the person who's asking the question of the AI model, right? On the other hand, you might want to use privacy preserving technology to protect the intellectual property in your model. So if you've invested hours or days or weeks or months in some cases of GPU or CPU time training a neural network, for instance, it's very interesting that the outcome product of that is a graph. It's just connected nodes and weights effectively. So it's a fairly small file is the output of all of that work for a long, long time. What's interesting is that, you know, if you want to take that model and perhaps run it at scale in someone else's data center, say a hyperscaler or a cloud provider, or even within your own organization, but perhaps another geographic location data center, there is some risk of intellectual property, your trained model, being stolen. And so one thing that you might want to do is protect the contents of that trained model by actually encrypting the model itself. And homomorphic encryption is one of the ways you could do this. So this rhetorical question, you know, what if your sensitive data, the data being sent to be inferenced on AI, could be protected? Or you could also think about it as, what if I could protect the intellectual property in the model? It's two different ways of using privacy preserving AI. And again, the technique I'm talking about is built on homomorphic encryption, which generally isn't just an AI tool. You can actually do arbitrary compute. So anything you could have written in software today, in theory, you could write a homomorphic encryption variant in terms of it being a Turing complete construct. The practical reality is, because of the way homomorphic encryption works, some things are more difficult than others. And so you have to sort of understand what the limitations of the technology are today. So let me go a little bit deeper beyond this rhetorical question. So what do we know about homomorphic encryption so far, and what should we take away by the end of this talk? Number one, it's technically achieved by actually doing the compute on encrypted data. We're going to talk about what that means, because a lot of us have a conception of how encryption works that's based on, you know, protecting man-in-the-middle attacks or something like that. This is fundamentally a different way of using encryption. Okay, so point number two, it enables processing of data without giving access to it. I, as the data owner, can encrypt some data, send it to you as a third party who has an encrypted view of it only and never sees the decryption keys. And you can provide business operations on that data without understanding the intermediate results that are going on, and ultimately compute an encrypted result, which makes no sense to you as the data processor. But if you send that back to me as the data owner, the person who originally encrypted that data, my decryption key will unlock that data, and that result will look to me just like the entire process was done as we do it typically today. And so that's the idea here, is that you can do processing of data without actually giving access to it. That's the fundamental breakthrough here that we're talking about. Point three, some people who want to get technical about it, it uses a technique or is based on the mathematics of lattice cryptography and the hardness of certain lattice problems. So we like to say that lattice cryptography is a type of quantum resistant cryptography. And before anyone gets too alarmist, you know, we shouldn't be concerned that within the next 6 months, quantum computers are going to break RSA or typical encryption that we know about today. But there is a hypothetical future where we build quantum computers that are able to crack existing quantum schemes. As it turns out, with lattice cryptography underpinning homomorphic encryption, it should be deemed safe. In other words, we know of no special advantage to having a quantum computer to cracking homomorphic encryption, unlike the advantage that we see for a quantum computer that was theoretically perfect and had good qubits to cracking more traditional types of cryptography that we might use today. And so lastly, this is just something that a term or a phrase that some of us came up with at IBM when I was back working with them. It's really about resolving this paradox of needing to know and needing to share. We recognize that businesses, you know, for AI and data science, you often need to know the data to do the data science or the AI that you want to do. At least traditionally, that's how we've looked at it. But also businesses are increasingly aware that in order to unlock the value of their data, they must combine it with the data of other third parties and so forth. But how do you resolve this? You want to protect your data and protect your clients and customers' data and keep it secure and safe. But you need to sort of intermingle that data with other parties in order to truly unlock the value. And one way that you can accomplish that is homomorphic encryption. And again, there are other techniques. There's lots of different things we could talk about, but that's the main one for today. So let me just give a bit of a picture because it might help make more sense. So we know about standard encryption, right? There's encryption during transmission, which is analogous to that browser lock icon that we always see in the corner and we're trained to look for to make sure that if I'm sending data from a client to a server, that some third party cannot intercept that message and understand what I'm trying to ask for. I think we're all pretty familiar with that. We use that kind of encryption all the time. The other type that we're familiar with that's very common is encryption in storage. So my hard drive, for instance, on my laptop is encrypted at rest. So you encrypt tape data, archival data, files that remain encrypted when they're not being used. We're all pretty familiar with this, I think. It's table stakes for the modern enterprise to be using encryption during transmission, encryption during storage. But the problem that we don't address with these kind of encryption is that for most systems, virtually all systems, ultimately someone has to unencrypt that data to do some useful computation on it. So once it gets to the server, the transmission protection is dropped, it's decrypted, and on the server side, the data is in the clear. And so that presents a moment of vulnerability or a period of vulnerability on the server side. And of course, even when you encrypt stuff in storage, eventually if somebody gets a copy of encrypted data that's been archived and somehow can break that cryptography, that's a bit of a leak window there. So let's talk about what's missing here in this picture. And this is FHE, which is now we see that even while it's under compute, it remains encrypted the whole time. And by the way, I do want to add that you should not use FHE specifically as an implementation for encryption during transmission or in long-term storage. You should use other encryption layered with FHE, but FHE adds the value that you take the data, you encrypt it as the data owner. From that point on, no one except the data owner ever sees the unencrypted data, which is a pretty powerful concept. And I'm using the terms that generally come from the GDPR kind of terminology space, but I think everybody appreciates that the data owner is whoever has the data, is responsible for the data, and ultimately liable if that data leaks out or gets used in a malicious way or is not does not comply with regulation. So it's a fundamentally different thing to think that once the data has been encrypted, it remains encrypted at all times throughout the life cycle of value add, throughout the life cycle of compute, and the powerful business transformations that we're actually trying to do on that data, including things like sophisticated AI. So I want to talk real quickly about some high-level conceptual ways that you can use homomorphic encryption and that people have used in research and in some proof of concept and prototype systems. One of the ones that's very, very powerful is oblivious query. So if you think about this technology, one of the things that people would gravitate towards as a use case is the ability to make a database style query of a data set without revealing my intent. So for instance, when I was working at IBM with a wonderful team there, we put out the IBM FHE toolkit for Linux and for Mac OS, and we shipped a demo where you could look at countries and capitals. So you could ask a question of what is the capital of England, for instance, and you would get back London. In this whole process, the data resident on the server side of the application was fully encrypted by the data owner who uploaded it. The query that I was sending from the client side, my intent saying that basically I don't know the capital of England, which is London, that query is anonymized before it's sent to be matched on the server side. So the server is not learning anything about me, and I'm still able to ask the question and get the answer that I want, which protects my privacy and protects the contents of the database on the server side if it ever were to be hacked or exposed or somehow infiltrated, or someone could get into the system that's doing that, whether it's malicious intent or honest but curious, threat vectors, et cetera. So oblivious query, imagine a world where we could do Google searches, but Google couldn't learn anything about you in terms of mining you for queries that you've asked over and over and over again. The kind of spooky problem that we've all seen where we search for sneakers or shoes or something, and then the next 5 days we see ads for sneakers and shoes in our inboxes or on the sides of various web pages because they're mining our intent, learning about us, and then using it in the future. So oblivious query is very powerful. The second example I'll talk about is set intersection. So for the mathematicians and computer scientist types out there, or folks that have ever seen a Venn diagram, the overlapping circles, this is the concept, right? So let's talk about one use case. Let's talk about no-fly lists. So virtually every country around the world has a no-fly list of people who have been identified as not able to be put on airplanes for security reasons, et cetera. And we have a list of airline flight reservations that are made every day from all the airlines in whatever country you happen to be in. And so the set intersection here is matching the manifest of passengers to the no-fly list that are curated by governments or other agencies, or sometimes intergovernmental agencies, to ensure that people who should not be traveling do not board an airplane. This is a set intersection problem. And in fact, it's a problem that's well suited to homomorphic encryption. And beyond that one example, let's just take it even further. So that was kind of a governmental use case of trying to match data from two different places and figure out what that intersection is. But again, it's done blind. So the airline doesn't have to divulge the list of passengers that are going to be on the flight, which keeps the privacy preserved of all the people who have booked airline flights and all of that stuff. And the government agencies are the folks who are doing the no-fly list, sometimes even airlines who have passengers that shouldn't fly or have been banned from flying. They don't have to divulge their entire list, so they can keep those secret and yet still compute that match where they meet in the middle. So let's take it from a purely no-fly list kind of example to a more commercial example, right? Because a lot of the folks here are probably running commercial businesses. This is very valuable in co-marketing. So if you have, for instance, that same airline, but maybe now we want to do a co-marketing campaign with a hotel, or perhaps Uber or Lyft or some sort of taxi, car service that's in the area, where you could match clients who have booked a flight with a reservation for a car, with a hotel that's in the same place, without each of those individual companies giving up customer access data about this particular person. Like if I book a flight, I'm not really comfortable if my data was then shared with all the rental car agencies and all the hotel booking places. If I've individually booked them all though, and those companies were able to anonymously share my data and realize that I'm the same person and we have a discount program or some sort of value-added benefit from doing this combination, if they pass those savings on to me, I would be happy about that. But I certainly don't want the companies just blatantly sharing my data in the plain text. So in the upper right-hand corner, let's talk about a different kind of use case. So there's private data. Again, we know that the richness and complexity of data often gives uplift to better AI models. So the more data you have, the better data you have, you get better AI results. But increasingly, we want to train ML models on pretty sensitive data. And we have to be very careful that we're using data in ways that are compliant with regulations and laws, and that we're being fair with that data, et cetera. So a key aspect here is that if that data is sensitive, if we encrypt it first and then train the model on the encrypted variant of it, we're adding an entire new level of privacy and safeguards around our ML, which will help keep us in compliance. I'm not saying it's going to make you compliant with the letter of a specific law, but it's definitely something that helps you get to a compliant state of mind where you're not possibly leaking the data, or details of a very particular customer's information further down the stream of the ML processing lifecycle. And then lastly, the use case I want to hit real quick because it comes up in the media a lot is this idea of secure outsourcing. So if you've got some business process you want to do, whether it's running payroll, whether it's doing AI inferencing at scale, and you want to put it out in the cloud to ease adoption or do it at a broader hyperscaler kind of approach where you're now serving tens of millions of queries or inferences across your AI model, but in different geographic locations spread around the world. It is something that can help with that by protecting your data and protecting your model and allowing you to put even crown jewel encrypted AI, the things that you've spent the most time and energy building for your organization, and put that out there at scale with the assurance that it's cryptographically protected. And so this is a future that we can see with homomorphic encryption and some of the use cases that we might want to do, many of which involve AI or data processing, data science kind of workflows. So let's bring it back real specifically on the AI topic. I think what I want to emphasize here is that privacy preserving AI as a whole, which is bigger than just homomorphic encryption, maybe things like differential privacy, functional encryption, and others are in this family of techniques to try to really up the game of security as it relates to data science and AI. This is going to be massively disruptive. Again, my personal belief, and not speaking on behalf of my firm, is that once we have solid AI adoption, good MLOps type workflows, which we're happy to talk about, and then we get fairness into the models and ensure that we're doing that, the next major thing to do is focus on the security and the privacy of the data that's going in that to maintain that entire workflow and keep your personal data safe. We all would like that. So what can we do with it today? Inferencing use cases where you're asking a question of a model that has been trained in the plain text, converted into a fully homomorphic encrypted variant and run in production. You can ask encrypted questions of that encrypted model today at speed. Some great work done by IBM earlier this year. Actually did some really great transactional work from an encrypted database right through to do inferencing at scale in millisecond times to do inferencing. So the speed and performance is there. That was a particularly interesting credit card fraud detection example where the team that was working on it was looking for fraudulent transactions coming through a system of record and then flagging, which of those transactions may potentially be fraud. And when you start talking about being able to do that, with millisecond latencies or, definitely sub-second latencies, it's opening a world of possibilities that 3 or 4 years ago, the performance just was not there. But a lot of clever folks working on that, both from IBM, got a great team at Intel working on advancing some of this stuff. There's entire startups and ecosystems being built up around this concept of privacy preserving AI. We've got folks like Duality, Infer, some great folks at Zama, who are all working in this space to try to advance the art and get us further down the road. But inferencing cases are viable now. It's time if you want to start exploring that. Those are the realm of things that I would say you should look at first. We already talked about the second bullet point, protecting the IP of your classically trained model. So if you have a ton of time and energy into your classically trained model and you want to protect that against theft or sort of somebody stealing the intellectual property, it's definitely a use case we should explore and talk about with your trusted advisors and your technology partners. We've talked about protecting the privacy of data that's sent to AI oracles, this future vision of being able to use search queries or being able to ask AI to approve you for a bank loan or some other hypothetical situation where your data was kept private, but you still got the benefit of using the online AI system for an inference. And I guess now that we've talked about those use cases that are viable now or close to viable at scale in production, what I want to do is talk real quickly about the 3 barriers that are preventing this from taking over the world today, right? So if this is so great and you're listening to me and you're excited, here's the downside, the things that are preventing it from being super common. Number 1, the programming model is very different. So if you think about it, because the data is encrypted at all times, for anybody who's a computer scientist or a software engineer in the audience, you can appreciate that it would pose really interesting problems for programming. An example is writing an if statement or a while statement. The control flow is what we call it, where you say, if this condition is true, pick answer A. If it's not, pick answer B. The problem is that because you're encrypted at all times, you can't compare A and B the same way you would in a classical computer. So that whole model of programming that has just become the standard of the way everyone does programming, it doesn't work. It doesn't work today. And there's some folks working on that. There's some recent work that came out from Google on transpilers, and some of the startups that I mentioned are working on some pretty good technology to take high-level constructs like while loops and for loops and synthesize those into the statements and control flow paradigms that exist in homomorphic encryption. But the punchline is it's harder to program today. Even if you're a very competent programmer, it's more difficult than it is to just program in the plain text. So people are working on that, and I'm very confident in my outlook that we will get there with the APIs and the various tooling, compilers, debuggers, and things that will help do homomorphic equivalence. The second big issue that we've touched on a few times thematically is performance. Again, performance keeps getting better and better and better. We're talking about decades ago, things that took days to run, we can run in milliseconds now. So we're advancing on that front. In fact, the United States government's DARPA agency, the wonderful folks who brought us the internet, they're funding hardware acceleration through ASICs, dedicated hardware accelerators, which should yield for a particular AI use case about model training and inferencing around a 5 order of magnitude performance improvement. So it's 10,000 times faster in about the next 3.5 years or 4 years. So you can imagine that for that particular AI use case that's well specified in the governmental program, of which there were 4 different consortiums or teams awarded money to advance this effort, that 5 order of magnitude performance for that particular AI use case will probably translate into lots of other performance benefits for similar AI use cases, or some of these other cases like privacy preserving search, et cetera. So there's definitely a roadmap that's published, well-funded, and you can follow along with that. The program is called Deprive. If anybody wants to look it up, we can send information about afterwards. Just get in touch with Edgar and myself. So on the performance front, I think we've got a handle there. So APIs are coming, they're getting better every day. Higher level constructs to use AI techniques will be built. So you can just say, give me a logistic regression, just like we would in Python today. In fact, the team at IBM that I used to work with have done wonderful work in building a great Python API and programming language to really help bring up the level of programming to something much more familiar to data scientists and ML researchers today. So API progress is happening. We've got the good folks at Intel and other places doing performance to try to maximize every ounce of speed we can get to get more use cases viable. But this last one, regulation, there's a catch. So we all know about privacy laws and whether that's in the United States or the European sort of consortiums of GDPR, and then sort of new laws popping up all over the world. There's a lot of challenges about this. And one of the keys is that, in my view, the regulations need to be amended to have safe harbor provisions or clauses that allow homomorphic encryption to be used as a solution to some of these problems. So we're waiting for that to happen. But I think what needs to happen before we can have regulation changed is some standardization needs to happen. There's a lot of different schemes or flavors of homomorphic encryption out there right now, each suited to slightly different tasks. And I think as the APIs and performance kind of move forward, we'll have some new schemes developed, other schemes may be deprecated, but in the long term, we're eventually going to, I think, kind of focus on a few. We'll get some standards out there. And then once the standards are there, I think the regulation will follow. And of course, I think a lot of that will also happen when there's enough demand where technically the people at great companies all over the world, including the wonderful audience here from Latin America, have implemented prototypes that they go to their governments and say, we can do this safely and securely at scale, but we need regulation to change to make it happen. I think then we'll see the widespread adoption of privacy preserving AI based on homomorphic encryption. And again, there's other techniques, but we'll save those for the questions, I think. And with that, that's the end of my presentation. I hope it was of some value to take you through that. And now I'd like to open it back up for dialogue or questions.
Yeah. So if any of you have any questions, please, we have the Q&A there on the platform. And I know that this is new to everyone or to a lot of people. So don't be shy asking the question. It can be right. Yeah. This is a real time when there's no bad questions. Let me start. Absolutely. Let me start backwards then, because I have some questions. So standardization, right? That's always a big thing. So since this is kind of new right now, you have a whole bunch of players as always trying to get in there. So it's almost like a wild west right now, right? When do you think that that's going to be normalized? How long do you think it's going to be like 2 or 3 major players? Because as usually we want to see at least 2 or 3 options out there.
Yeah, so in terms of technologies, the schemes, so to speak, there are definitely 2 or 3 kind of emergent schemes that seem fairly popular. I'm not going to speculate on which one will win, but certainly CKKS is one of the ones that's really well known for the AI and ML workflows. It was developed out of South Korea originally for the research team. That one is really popular with a lot of the companies and firms and the practitioners because it has the capability of using floating point, which is really advantageous to AI type use cases. Okay. There's also a scheme called BGV and another one called BFV. And some of those schemes are integer based. So they're faster in terms of raw performance in some ways for certain classes of use case, but only in those cases where you don't need floating point numbers. And they each have a purpose and a reason for being. And there's actually a bunch of other schemes too that we could talk about. There's also like TFHE is one of the libraries that has a slightly different take on how to do this. And there's a bunch of different ways to go about implementing this technically. And I think that there will be some emergent victors, especially when we see the results of this performance kind of work that comes out. Because ultimately, I think if one of these libraries drastically outperforms the others, it will unlock enough use cases that will then make it kind of a de facto standard, even if it's not a literal standard. But I do want to say quickly that on the notion of major players here. I want to just say that the community of homomorphic encryption folks that are out there working on specifically AI or other applications of homomorphic encryption, all those startups, and I didn't mention everybody, there's like Eyes Up, and I don't have time to exhaustively go into the entire spectrum, but everybody from the IBMs, the Intels, the Xammas, the Duality, Infer, I mean, there's other folks that are doing stuff. Kornami's trying to do some interesting work with hardware acceleration. All of these great folks believe in the same vision of privacy preserving, right? And I think what's interesting is it's a community. And so even though some of these startups may be viewed as in competition with one another, my read on the community and just having met a bunch of these folks is that it's healthy co-opetition, right? It's cooperation and good marketplace competition, because ultimately we all want to see the same future where our data is safe and we're able to just stop having data leaks and all these things that just keep people awake late at night. But I think I do want to also mention the standards thing that you mentioned about the time frame. There is a consortium, homomorphicencryption.org, which has been trying to kind of bring together these parties over the last several years. Of course, COVID impacted a fair bit of that. But if people are interested, check it out. And I think we'll get there sooner rather than later. I can't put a time box on it, but I would think within the next 2 years, you'll see some pretty serious.
The demand is there. I mean, the demand for privacy, it's amazing. And it's not just one location. So you cannot see this, people in the audience cannot see this, but we have our next speaker already here. And he's asking questions, Mo, by the way. And so thanks, Mo. I appreciate you being here on, so early. He's got 2 questions. And one, any improvements impact to adversarial attacks? So labels will be encrypted, but wouldn't an adversarial attack still be possible even with homomorphic encryption?
Yeah, the most of the attacks that you read about for homomorphic encryption at this point are like chosen ciphertext attacks, where somebody will try to specifically craft a message and then try to encrypt it and get the same result. But one of the interesting things about homomorphic encryption is that it's the encryption scheme is non-deterministic. So if you take the same value, letter A, and encrypt it 3 times in a row, you'll actually get 3 completely different values that through the magic of the implementation of the system end up resolving to the same thing through the modular arithmetic tricks and all the other stuff that kind of make it work. So chosen ciphertext attacks seem to be one of the big threat vectors where people will try to find an unencrypted message in the encrypted variant and try to work backwards how that goes.
Yeah.
In fact, there was an issue with the CKKS scheme that I mentioned earlier in this discussion. I think it was late last year or 2 years ago, where there was actually a paper published out of a group in California who found in the wild all of the existing implementations were susceptible to one of these particular chosen kind of attacks. But that particular threat vector could be mitigated by source code changes, which happened immediately from the academic community, alerting the crypto community early. And so everybody patched their libraries and systems, or I should say most did. And once the libraries are patched, it's about good hygiene, right? Don't leave around unencrypted data with the encrypted version right in the same place. So it's like, yes, it's an attack, but in the same spirit, it's also like homomorphic encryption is not the silver bullet. And in fact, this was one of my things that I'm glad we get a chance to talk about right now. Don't believe the hype when they say take your unencrypted data or magically encrypt it and then just trust it in the public cloud, right? Theoretically, yes, that's what homomorphic encryption lets you do. But here's an interesting take. Homomorphic encryption lets you do arbitrary compute on encrypted data. So it means if Eli encrypts his data and sends it to Ed, who's going to compute on it, if Ed does what I expect, it's fine. But it means that anyone else who has access to that encrypted data, by definition, could just multiply everything by 10, an encrypted 10, but could just tamper with the data. Tampering in the sense of they don't know what they're doing, but you can manipulate the data, because that's the whole point, is you don't need private keys to manipulate the data. So you have to take homomorphic encryption and layer it with other technologies to keep the tampering part down, right? Homomorphic encryption protects the integrity of your data, protects the privacy of your data in the sense that it's never revealed. You also need integrity protection around that as well to keep people from just tampering with stuff. So I want to be very clear, homomorphic encryption is awesome technology. It enables some great AI use cases, but you also need other traditional security mindset and model for real deployments. Hopefully that answers the question that Mo asked for the first part about the chosen attacks. Or
I think so. Yeah, and he's listening, so he'll let us know if he didn't. Yeah, he says yes, perfect. And then he's got another question. He says, I'm a mathematician. So as the name naively suggests, you construct a relationship preserving homomorphism to encrypt. So it is a one-to-one, non-destructive. If so, could it be learned, guessed?
Yeah, the learning and the guessing, sort of that comes back to the fact that it's got an error quotient that's added along the way for every time. So working at it backwards and sort of guessing it is extremely difficult. It's actually tied foundationally to problems with lattices in terms of finding the distance in a lattice field. But the idea is that effectively, the way it works, just to give some context, is you take your data, you convert it into the bit stream that represents that data, and then you shatter that bit stream into little tiny chunks of bits, and then you sprinkle those bits across the coefficients of an extremely large polynomial. So this is how it actually works, right? So you take the letter A, B, C, and you split that into the ones and zeros that make up the bit stream. Some of the ones and zeros go to the front of a really long coefficient polynomial, some go in the middle, some go in the end. And when I say a big polynomial, you think back to middle school when you ax squared plus bx plus c. That's what we think of when we say polynomial. What I mean here for homomorphic encryption, that polynomial instead of 3 terms, A, B, and C.
Eli?
Hundreds. Yep.
Okay, there you go. You froze there for a while. You were talking about polynomial, and then you froze.
Apologies. Hopefully I'm back. So I was just saying that the ax squared plus bx plus c kind of approach, that's a 3-degree polynomial, 3 terms. When we talk about homomorphic encryption, it could be 10,000 or 50,000 or 100,000 terms. So we're sprinkling the real data throughout this massive polynomial and using modular arithmetic at the end to sort of take away all of the polynomial junk, leaving only the bits that matter at the end. So anyway, I hope that helps for the mathematicians. I know it's not a rigorous proof, but look into it. There's a lot of good papers about it.
So here's a question from someone here, from Andres, my co-host. He says, basically, the challenge is more than to do with ethics, right? How ethical you are in the use of data. I mean, you just said, right, that you encrypt and you give it to me, but doesn't stop from somebody else to come in and do stuff with the data that they're not supposed to be doing and affect the data. Yeah,
the relationship between privacy and ethics is kind of a nuanced and interesting one if you think about it. So one way that you can look at the combination of privacy preserving AI and ethics is that if your model was trained entirely on encrypted data, then in one way you could say that you can't intentionally bias anything by sort of people choosing only the data that they want to choose and then say, let's train the model on this. So you're doing some implicit bias by saying I only took data from this subgroup of people, right? So if the model training was done fully encrypted, in a sense, it would be blind from the data. So there is a potential way to help with the ethics, but ultimately, whoever chose the data to go into the model, if they screwed it up before you encrypted it the first time, it's already done. Like the well is poisoned, so to speak. And then in terms of using the model, one thing that I do think is interesting about ethics is that it makes the model that's doing the inferencing or the oracle that's answering the question, it has no visibility into you. So let's say we're doing a credit card loan application, AI model. It's a quick first pass pre-check for a loan, maybe. What's really nice is ethically, if I'm submitting my intent to sort of maybe ask about a loan, I'm not leaking the information that I might need a loan, right? Which then somebody else could be predatory and take advantage of me and say, well, hey, you were declined, but let me give you a loan for a much higher rate than what we would normally do because we know that you were declined and we know that you might be needing a loan. So there's some ethics there in terms of just because it's double blind, I think it could benefit some of that stuff, but they're separate issues that are interrelated in a complex. I guess is what I'm trying to say.
Right. Another thing that I have here, and I think you already asked that, ML on encrypted data. So, so by default, it means that FHE should be used, as you said, with other encryption mechanisms, right? It should not be throw this one away and just use FHE. I mean, correct. FHE works. Okay.
Yeah, you definitely want to combine the right encryption technology. And this is general about security in general. You need to pick the right technology for the right threat vector, right? But if you want to start dabbling with machine learning and homomorphic encryption today, there's a bunch of good things. Like IBM has a wonderful toolkit that I mentioned. Intel has a toolkit they put out as open source. You could start picking up this stuff and writing applications today. It's really when you want to take it at scale and want to put it into production that you need to be very aware of what threat you're protecting against and layering the right security. And there's plenty of people, plenty of consultancies, plenty of companies, plenty of technical folks within your organization that will help.
Exactly. So government, if this works, right? FHE works, seems to be working. Let's say it's adopted in 2 years, as you said, right? The technology catches up and everyone starts using it. It seems like, as you said, the privacy things, right? The oblivious query, the set intersection, and the other 4 points, right? It's taken care of. Oblivious query is the one that we're more familiar with, right?
Yeah.
Right. So those are things that the big companies don't want to give up. They're gonna lobby the heck out of the government for that stuff. So how is this gonna happen when you have such a barrier, powerful companies going no?
Right. That's a good question. So, and I mean to throw no disrespect at companies like Google.
No, that's fine. That's fine.
But we all know that their business model is based on our data, right? What we give them becomes the product. They give us a service in exchange for our data. They then value add that data and either use it for marketing or whatever they do to make their money. But you can imagine where that's a field that's ripe for disruption. If someone can come along and say, I can provide Google search results or Google Maps functionality without learning about, like, let's use the Google Maps example. Yeah. I'm going from here to there and I want to stop at an Indian restaurant on the way or something, or maybe I want Thai food, or I want something from
Colombian food,
Colombian food, right? Yeah. So I'm taking this trip and I want to sort of stop. When you ask Google for that with Google Maps, it knows where you are now, it knows where you want to go, so it knows your intent, and it knows what you're interested in, so it can market at you in the future. You can actually provide that same experience today if somebody wanted to build the app that was entirely privacy preserving. So what I think is going to happen, and this is again me speculating, there will be a class of company who takes privacy seriously. I mean, I can give an example of like Apple, for instance, has a bit of a brand for taking privacy seriously. If they were to build privacy preserving layers into their default apps, I mean, you buy the phone, so you get the premium experience, and they don't mine you for data, because the model is they're selling you the hardware at a premium price or selling you the service at a premium price so that you're not the product. Google is the 180, which is like, we're giving you a lot for free, but we're mining you for data. So I think what you'll see is these technologies may embolden some of the privacy preserving or focused companies and would be potentially disruptive to the ones that are doing it for free. But it's a spectrum. And again, just as shout out to Google, they just did some wonderful work about a homomorphic encryption transpiler. So they're very interested in this work too. And I don't mean to throw any bad connotation. They're just the example that everybody knows about.
Right. I mean, this is all about choices, right? Again, in the panel yesterday with the people from, focus on fintech, that was the question, right? About privacy. People want privacy, but they don't want to pay for it.
Yes.
So, but there's some people that want privacy and want to pay for it, but there's no option for those people. So
that's what it's about, right? So, and I think there's a lot of cases where we just don't care. If I'm honest, like even the most privacy preserving zealots amongst us, some data we don't care if somebody learns about us. Other data, my financial transaction history, my healthcare data, anything that falls into regulated industry today, I think that's where you're obviously going to see the biggest impact with homomorphic encryption or privacy preserving technology, and by extension, privacy preserving AI, because there's reason to protect that data legally, ethically, morally, and for all the right reasons. That's where people do want their data protected. Some of the stuff like maybe Google Maps, I don't know. I mean, maybe that'll always just be free and we'll give that information away because it's an exchange we're willing to pay. With my healthcare, it's not an exchange I'm willing to do, right? I want my medical data safe, my genomic data safe, my financial history safe, you get the point.
So right now in the world of cybersecurity that we're all living in, the biggest issue is ransomware. Right? Put your future thinking cap on, and in 2 years, 3 years, FHE, it's out there and it's working and people are buying it. How effective will FHE be against ransomware? Because ransomware is going nowhere.
Yeah. That's a good question. So my gut reaction, I've never been asked this question, so thank you.
Oh.
I would say that there's two kinds of ransomware I'm vaguely familiar with. One is the type that will lock out your systems until you pay for it to give you access to the system again. FHE is not going to solve that problem, so it will not help that. But the other type of ransomware, where they basically say, we've broken into your machine, we've got copies of your data. If you pay us, we'll destroy the data and give you the system back. There is a class of malware that falls into that category. In that case, I think you got to win. I think homomorphic encryption here, if you were using homomorphic encryption at scale on that system, I don't care if you have the data. I freely give it to anyone because it's encrypted and you can't break it. So unless you have my keys. So this goes back to the point of your cybersecurity folks will tell you, okay, this is only as strong as your key management system. Yes. So I encrypt my data. I can leave it out there in the Wild West. Anybody can play with it. Anyone can manipulate it. I'm only going to trust the people who've manipulated it, that have layered the right security so I know it's not been tampered with. But if I leave my keys laying around, then it's game over, because now they have the data and they can find the keys, they can decrypt it. This is basic, security hygiene, but people have to be aware of it. But for that class of problem, where they're holding you ransom because they think they've stolen your valuable data, well, if the data was never in the clear and I was responsible and never left the keys on the same system, or in another vulnerable compromised system that the hackers got intrusion to, that side of the malware threat for I think it's gone, or at least drastically mitigated. That would be my read on the situation.
Okay. So you mentioned that DARPA is involved a lot. Yeah. And we know when DARPA gets involved, things usually move along pretty fast.
Yeah.
Any other governments being
That's
involved?
That's a good question. I mean, I can't speak authoritatively, but I would not be surprised if certain governments in Asia are probably doing some sponsorship, directly or indirectly, of this technology, because it's, and I should say even in the US and other government, I don't know why I specified just Asia. I guess I did that because like South Korea has a strong history and a huge,
well, they already have a
they've got a deep talent bench of academics like in the space. So if they're doing, and I don't know how their education system works, but if it's partially subsidized by the government, in effect, that you have folks being trained to do this stuff. Large places like China, clearly they have an interest in all cybersecurity stuff. So it's on their radar. They're looking at it. And I've seen a lot of papers actually coming out, papers and patents actually coming out from like the Tencent group, the Alibaba family of companies, huge volume of patents. So I know there's huge interest in the Asian markets for that. And obviously like the United States government, if it's security related, there's probably somebody in Langley or in one of the top secret.
Yeah, exactly. Military already involved.
Yeah, but I think I think DPRIVE awarded something on the order of around 10 to 15 million US, if I remember correctly, to each of the four recipients of this challenge. And so it's a fair bit of money. I mean, 15 million per category times 4. That's a one-time 60 million roughly US investment. I am positive other companies other companies have received money from governmental stuff, and I'm sure there's been some governmental contracts, but I'm not privy to any of that information. I'm only speaking based on public information.
Right, and based on like we're running out of time, but based on your experience, who do you think which vertical, which market it's shows a lot of interest and it's moving more? Is it the healthcare industry? Is it financial industry? Which one it's driving this?
I'm bummed you phrased it that way, because I don't know which of the two. But if I had to pick across all verticals that I know about, I know that there's huge interest in fintech, because fintechs are disrupting the way we're doing banking. There's a huge amount of money in the space. There's a huge amount of regulation in the space. Fintechs, specifically in the financial sector, are really looking into this, along with more traditional financial firms. Healthcare,
but definitely fintech, because they're not legacy bound.
They're at a position where they can be forward looking, because a lot of them are still burning through investment capital and have a roadmap of 2, 3, 4 years, which aligns well with the tech. On the healthcare side, there's a ton of interest in centralizing things like medical imaging cases and things like that are well publicized, where people would like to take their data from a local hospital perhaps somewhere in Colombia, for instance.
Mhm.
You go to your local clinic, you get an x-ray or something, and then maybe that gets sent to somewhere around the world,
Yeah.
fully encrypted, to have it examined by AI to look for bone fractures or some other thing.
Yeah.
That's a case that comes up a lot. But I think financial and healthcare are the two biggest, but also a surprising amount of interest across verticals in logistics and supply chain challenges, which are weird because it's competitive trade secrets with big money behind it, because everybody has to secure their supply chain.
Yes.
Everybody wants to keep their supply chain a secret. There's a lot of interest in that space too, which a lot of people don't think about.
Wow, that's pretty good. Well, Eli, thank you so much for your time. And this conversation's always go by so fast. It's unreal.
Oh, I know. I wish we had more time because this was great. And thank you to everybody who asked good questions.
No, this is great. So appreciate you being here, and looking forward to hosting you in the future.
Sounds good. If everybody out there has any questions or anything, feel free to get in touch with me on email or through any way that you can find me. I'm on the internet. I'm easy to find on LinkedIn. And I look forward to talking to a lot of you folks about interesting applications and use cases in the future. Thanks so much.
Thank you so much, Eli. Thank you so much.